So I will explain here how we look at climate models which take into account radiation, the greenhouse gases, which include water vapor, thermal equilibrium, and convection. Um, and, uh, and this is the basic model that Manabe and Weatherald in 1967, this was the most influential climate paper of all time, as it's been called, and that won the Nobel Prize in Physics in 2021. So it was the first paper to model what happens when we have carbon dioxide in the atmosphere, heating it up, and that carbon dioxide also then leads to water vapor being evaporated more into the atmosphere and creating more greenhouse gas effect. So before that, the models had just used carbon dioxide and didn't take into account water, but Manabe and Weatherald actually included water vapor into their models, and they got a more, what they thought was a more rational value after they created these models. So let's explain a little bit how these models work, how these climate models work, and what is the crucial thing that's missing that's been pointed out by Anastasia Makareva, which is that there's a certain critical lapse rate. There's a certain parameter in the model that's set as a constant where really it should vary if we increase more vegetation into the models. And so these models perhaps do not really carry the right values because they don't properly take into account the impact that vegetation has on evaporation, cooling, and this effect is not taken into account. And if it was, then deforestation and chopping down of trees and the lack of evapotranspiration could have actually changed the temperature on the Earth to heat it up. So let's explain a little bit. So in terms of the radiation and the greenhouse gas, so there's two basic pictures we're going to look at, the radiation picture and the thermal equilibrium picture, and this is also a radiative equilibrium picture. And so this takes into account the solar radiation as it comes in, and some of it also comes all the way in here. So what happens as the solar radiation comes in is that it gets absorbed at each layer as it turns into the infrared radiation when it comes through, and so so as the solar radiation bounces off the Earth or is emitted by the plants and the soil as thermal radiation, it hits this radiation layer, this level of atmosphere, and then some of it will bounce back depending on how thick the greenhouse gas is. And re-radiated. It actually radiates in all directions, but for simplicity, let's assume it just bounces back. And some of it actually goes through, and then it bounces back and forth, and some of it then increases and flows out to the atmosphere. So this is the basic radiation picture. And so at each level, we actually have to calculate how much it's radiating, and that's proportional to this T to the 4 number, the temperature to the power 4, which is called the Stefan-Boltzmann. And so we actually have to calculate how much each level of atmosphere radiates. And then we can actually come to a certain equilibrium value that the Earth's surface temperature will take, depending on how much greenhouse gases. So if there's more greenhouse gases, you actually end up calculating a higher value for the temperature of the Earth here. So that's the radiation picture. But we also have to take into account thermal equilibrium. And this means that the higher up we go, there's less gas molecules, it gets thinner, and so the pressure is less, and then the temperature is also less, because as the molecules fall down, they can actually gain speed and have more kinetic energy down here, and so the temperature is higher closer to the Earth. So we can actually plot this temperature versus height, and so this is when there's not taken into account water, and then if you do, it's called the dry lapse rate, this temperature profile, and then I've drawn it maybe a little too steep here, but this is the moist adiabatic lapse rate. This is the temperature profile when you take into account water, because as you go up, if there's enough water that goes past the dew point, it will heat up this atmosphere at each point, because when the water vapor condenses out into liquid water, it releases some of the latent heat that's stored, and so it heats up. And so the temperature profile when there's a lot more water in the atmosphere is going to be less steep. Now, in our climate models, it's hard to actually model non-equilibrium states. So it's much easier if we can assume everything's in equilibrium, like it's stabilized. So what happens if the temperature profile is too steep, if it's actually steeper than this value, then what happens is that it'll get colder much faster as you go up. But then a parcel here that's warmer at the bottom, an air parcel, will actually want to rise because it'll rise a bit because it's hotter. But once it gets to height, it's still hotter than the surrounding air because it's getting so much colder, this lapse rate. So it'll just keep rising. So what you'll get is convection. And so if it's past what this is called the critical lapse rate, if it's steeper than this slope, then we'll get this unstable convection. And we want to actually just model the whole picture in terms of equilibrium. And actually Manabe and Weatherall's model, they call it the radiative thermal equilibrium model, or radiative convective equilibrium model, meaning that they've equilibrated everything. And so we actually want to find this critical mass, the critical lapse rate, and just set it at a constant in our models. And so they went looking for this. So in the models, what happens is that whenever, so what happens is that you have this temperature profile of what the air is doing, and then as you add in the radiation, it actually makes it steeper and steeper. So the radiative part of the thing, because basically the radiation will create more heat because of the greenhouse gas close to the Earth, and so it actually get hotter here and cooler up there. And so this slope becomes steeper and steeper when you add in this radiation effect. And so as you add in this radiation effect, this slope gets too steep. And so in the models, what they did was that they just said, okay, we're just going to keep it at this value, even though if it unequilibrates. We just assume it's going to, over much longer period of times, we'll actually go back to thermal equilibrium. And so that's how they did the calculations. But you also need this value. And so when they put into the model, they got certain values. So they calculate the lapse rate from the models. And so this is an example, just as a, just to throw into some example numbers. They might calculate 90 degrees Fahrenheit as at the Earth, and then it cools down to 37 degrees Fahrenheit further up. But the actual value when measured might have been actually like 85 degrees Fahrenheit and 38 degrees. So they calculated too high a number at the Earth and then too low a number further up. And so, and so they actually had to put in this actual number that's experimentally valued into the system. So there's some So they calculated actually some numbers that seem to agree with what experimentally was measured, and so that's why this paper got so much attention and ended up winning the Nobel Prize. But Anastasia Makareva has been pointing out that we shouldn't really be using a static lapse rate because what happens is that if we did add more vegetation, say, then it should actually cool, and this lapse rate will change. Or if we actually deforest it, then the lapse rate will you actually get hotter here and then cooler up here. So you actually be changing the lapse rate, and so this is the problem with their model. So how did they use their model? So what they did was that they inputted this critical lapse rate into their model, and then they varied. So then they said, what happens if we vary the carbon dioxide? Because carbon dioxide is the forcing parameter that they're looking at. So that they added more carbon dioxide, which then lead to more evaporation because the air is hotter. So there's more water vapor, which then led to more greenhouse effect. So there's more greenhouse effect here. And so then this changed the whole temperature profile even more. So this would heat up, and the profile would be like this. But the problem is that what we should really get is something like this. If we add more vegetation, we should actually, instead of getting like 85 degrees, we should actually get something cooler, 84 degrees here, instead of 38, 39. So the problem is that climate models cannot really adjust for this. And part of the problem is that because they're using equilibrium, and in equilibrium models, we can't have this value go past that, because then the whole model becomes unstable. You have air parcels rising, and so that's the basic issue. So these radiative equilibrium models and also a lot of the global climate models right now, they can't really have a good way of dealing with it because they can only deal with equilibrium situations for the most part, because the grid size of the global climate models is about 60 miles or 100 miles, and the convection is much smaller scale, like 1 mile. There are some dynamic models that take into like this convection model, actual rising, but it's at a much smaller scale. They can't do the whole Earth. Maybe just on a small 1 kilometer sky scale, you can actually model this, but then you're not modeling the whole Earth, and so that's the problem right now. That basically all these most of the global climate models, they have this issue right now, is that they assume the critical lapse rate is static, when really if you're going to change the vegetation amount, then that critical value should change.